All right, so next week we're going to move on and discuss Newton's laws. But before doing so, I wanted to revisit Fermat's least time principle. Okay? And why are we going to do that? Well, I want to give you some reasoning that you may be able to apply to what we learn next week with Newton's laws. So I put back up the table Ptolemy's data from 140 AD and Snell's fitting of that data. Right now, just want to point out what he actually fit, right? Usually you see this written a certain way, but really this is the way to look at it. And even more properly, it's a ratio, right, of sines of the angle of incidence to the angle of refraction. And what Snell found was that when he took the sine of 8 degrees and the sine of 10 degrees, right, he would find that he got a constant here. Right? And from taking real-world data, so really Snell's law was an observation that if you take the sine of the angle of incidence to the sine of the angle of refraction, then you get a constant in. Right? And if we're going from, say, material 1 to material 2, when we observe this refractive angle, then we could call this in 1, 2. And so what I want to do now is consider three possibilities. Basically air interacting with water, right? So we'll say 1 is air. I'm going to write this a little bit bigger. I noticed in re-watching some of these lectures that the writing is a little small and hard to see. So we'll say 1 equals air. And so here we would, of course, have angle of incidence, and we would have our refracted angle, theta sub r. And then 2, I'm going to let that be equal to water, H2O. And so this would be characterized by an index in 1, 2, which is the ratio of the sines of the angle of incidence and angle of refraction, right? Also consider an interface between air and, say, material 3, which we'll call glass. Right? Again, have a refracted angle, have some incident angle. Right? And finally, we can make a third measurement between water and glass. This would be in 1, 3, and this we could write as in 2, 3. Now, just using Snell's law, right, there's no reason to suspect that in 1, 2, in 1, 3, and in 2, 3 are connected in any way whatsoever, okay? However, using Fermat's least time principle, right, we can actually make a prediction that they are connected in a meaningful way, okay? And so how does that work? Well, we can write that in 2, 3, this third measurement, right, the refractive index that I observe when I go from water to glass, right, that index can be written as the ratio of velocities. Because remember, under Fermat's principle of least time, right, the index of refraction is the ratio of the velocities. So this is the velocity of light in water over the velocity of light in glass, right? Yes?
Yes.
Okay? And that's what this index represents. But we can rewrite this, right, as, let's do it that way. So we'll say, you know what, we can take V2 over V3 and multiply that times V1 over V1. Yes?
Yeah.
Because that's just 1. You can always multiply anything times 1. That's the velocity of light in air, okay? Divided by the velocity of light in air, which of course is going to be 1. I can rearrange this, however, right, to be like this. V2 over V, actually I want to do it slightly different, sorry. V1 over V3 times V2 over V1. So it's just association, right?
Yes.
But this is the same thing as V1 over V3 divided by V1 over V2, right? Because when you divide by a fraction, you can multiply times the reciprocal of that fraction instead, right?
Yes.
So all I did is just flip V2 over V1, turn it into V1 over V2, and switch this to division. But this is just V1 over V3. I'm going to write the fractions a little bit differently now, right? Over V1 over V2. Yes?
Yes.
And by this convention, right, N12 is equal to V1 over V2 under Fermat. N13 is V1 over V3. And N23, of course, is V2 over V3, using this principle of least time, this idea that light travels at different speeds in different materials, right?
Yes.
V1 over V3, well, that's just N13, right? And V1 over V2, well, that's just N12. And so what do I have in the end? I have this relationship, which we did not have under just Snell's law, that N23 is equal to N13 over N12. Which means that if I know the index of refraction in this one, N13, right, when I go from air to glass, and I know what it is when I go from air to water, then I can predict what the index of refraction is going to be, or really the ratio of these signs, right, for water glass, okay, which I could not do before. So it falls out directly from that. And that, you know, is surprising if all you know is Snell's law. But under Fermat's principle of least time, it makes sense, right? And it makes sense because of this argument about the ratio of the velocities, right, being equal to the index, so the ratio of the indices, right?
Yes.
So we have a new prediction, okay? And so this kind of reasoning will be useful next week when we start on Newton's laws, okay? But I just wanted to revisit this and point this out to you before we move on, so that you can have that in mind. And so when we start talking about ratios of accelerations next week, you should be thinking about Fermat's principle of least time, okay? And be reminded of the thing that he found there, okay? So that means that there's some intrinsic material property, right?
Yes.
About material 1 and material 2, right? And material 1 and material 3, right? And if you know this intrinsic material property for 1 and 2, and also for 1 and 3, then you can predict, right, through some equality, what the relationship of 2 and 3 will be, you see?
Yes.
Okay, any questions on that? That's pretty much all I have on this. This closes out our discussion of geometric optics, where really we wanted to iterate the idea that there's this simple principle, right, that light is this thing that travels in straight lines, right, and that the only time it bends or changes its course is when it encounters a material interface, and the material that it's entering travels at a different speed, or the light travels at a different speed in that material. Then we'll get some bending, okay? But other than that, it's just straight lines, okay?
Okay.
And we'll find when we get to Newton's laws and we start talking about particles instead of light, that these things will follow much more complicated trajectories than straight lines, okay?
Okay.
So that's why I wanted to spend some time talking about geometric optics. Okay?
Okay.
No questions, Gabe? All right. We'll close this out then.